Okay, hey there, everybody. It is Thursday morning, 9 a.m. Pacific time, and you know what that means. It is time for OpenCV Live. We will get started in just a few minutes here. We've got a real fun episode. This is part 2 of our series, what turned into a series on simultaneous localization and mapping, because there's just so much of it out there. But as is tradition, please let us know where you're coming from as you filter in on YouTube, Twitch, LinkedIn, or Zoom. I am coming to you from the friendly confines of On-Base Production in beautiful downtown Niles, Michigan. You can hear the traffic behind me out there. People are getting started with their day. I've got a latte here from 2nd and Main here in Niles. We'll be getting started in just a few minutes, but drop where you're coming from in the chat. Satya, where are you joining us from today?
From San Diego, California. The weather is perfect today.
It's pretty damn nice here in Niles as well. I think it's about 75 out there. It's a little bit warm for this time of year. Ali, where are you joining us from today?
So I am from Iran, Tehran right now, and it's a little bit cold now.
What's a little bit cold for Tehran?
What temperature is it?
Yeah, what's the temperature?
The temperature here is like, let's say, 20. Yeah, almost. I'm not sure. In centigrades.
Okay.
Gotcha. Yeah. Gotcha. All right. Let's take a look at the chat. We've got, I'm not even going to try to pronounce this name here, but chiming in from New Orleans, Rakaya, Mustafa from New Orleans, Nolans, a great city, a really fun, one of my, probably, honestly, maybe my favorite city I've ever visited. We've got Bart saying hi from Amsterdam. Over on Zoom, we've got East Grinstead, United Kingdom. That is an extremely UK name for a place. We've got Sinian from London. We've got Jari from Finland. We've got Carlos Nava he says, good morning, greetings from Baja. It's hot as hell. I believe that. We've got Bruce Wright from Calgary, Alberta, Canada. Steve Simpson from Smart Mansion in Toronto. We've got Seth from Cupertino, California. We've got Doug from Fort Lauderdale, Florida. Jamal from the United Kingdom. Parthasarthi says, hello from somewhere in the sky via Starlink on the way to San Francisco. Okay. We've got, I'm imagining you just like riding a satellite right now. We've got Jim from Bali. It's midnight and 25 degrees Celsius as usual. I've heard Bali is
as usual.
Yeah,
nice.
I've heard Bali is fantastic.
Yeah.
But please, let us know in the chat wherever you are joining from. We've got Kaya. Hey, how's it going? Okay, I see you. Kaya, that's how you pronounce the name there. We've got Taha from Turkey, or Turkey, I think they're trying to call it these days. Looks like folks are finally picking up over on the YouTubes. Good news, a little bit of inside baseball before we get started here. We're now monetized on Twitch. And so we will maybe a little bit later in the episode talk about how you can, if you are an Amazon Prime subscriber, you can give us free money basically by giving us you have a free Twitch subscription that you can give to any Twitch streamer, and that means you can give it to us, and we'll get a couple of bucks from Jeff Bezos for free. So, free money is always good.
Are you going to show us how that works? Because
yes.
Okay.
We will show a little bit later in the episode. I don't want to take up too much time at the top here, but we will definitely show a little bit later in the episode. Checking in on Zoom one more time. We've got Francesc from Catalonia. We've got Balveer from Punjab, India. We've got Montas from Lithuania, where it's 8 degrees Celsius. We've got Dooley from Angola. Thanks so much, everybody. We've got Stefan from Vancouver as well. I think we can go ahead. I'll solo you, Doc, and we can go ahead and get started.
Hello, everyone, and welcome to OpenCV Live. I'm Dr. Satya Malik. Simultaneous localization and mapping, or SLAM, remains one of the most active and difficult areas in computer vision and robotics. Should you use purely visual SLAM? Do you need to use LiDAR? What about indoors and outdoors use cases? They are different. On today's episode, we welcome back OpenCV community member Ali Pahlevani of SLAMbotics for part 2 of our look at modern SLAM implementations. This time, topics will include RESPLE, KISS-SLAM, MOLA, Roman, and more. But first, with me, as always, is OpenCV Director of Content and Creative, Phil Nelson. Phil produces the show. If anything goes wrong, it's his fault. Good morning, Phil.
Yes, good morning, Doc. Good morning to you out there. It's me. It's PHI-LLIP. I am your co-host with the co-most, the second banana who's second to none. I'm also your plus one and only. It's Mr. Nelson, if you're nasty, but you can call me Phil. And I'm here to remind you a few things we do on every single episode of this here program. The first of which is a giveaway to you in the audience. Stick around a little bit later in the show. I'm going to ask a trivia question based on the presentation from our illustrious guest. And the first person to answer that trivia question correctly will win the OpenCV University course of their choosing. You can see what courses are on offer by going to opencv.org/university. Invest in yourself, upskill, get a new job, get paid more at your current job with OpenCV University. We're also taking questions from you in the audience. Use the Zoom Q&A button if you're watching on Zoom. That helps me organize those. Or if you're watching on YouTube, Twitch, LinkedIn Live, elsewhere, just ask in the chat, and I will do my best to surface the best questions and bring them up here on screen. Before we get started here, we've got a quick bit of business I would need to remind you folks of. OpenCV is a nonprofit organization that releases open source software, and as such, we depend on the support of companies like our members and partners here. We've got, I want to do a big thank you to our current members and partners. Before we get started, ARM, RunPod, Intrinsic, FutureWay, JetBrains, RoboFlow, Hackster, 7th Sense, Google Summer of Code, OpenMV, Orbic, the British Machine Vision Association, our newest silver member. Welcome aboard, folks. We've got 10-gram vision, Amped Software, Intuitivo, Rerun, the Edge AI and Vision Alliance, and Big Vision, because every company needs a big vision. One of the ways you can support OpenCV is if you work at a large organization or a small organization that benefits from OpenCV, encourage them to donate and become an OpenCV member. The easiest way to do that is by going to opencv.org/support, or you can just email me, phil@opencv.org. If you're just a regular person, a normie, if you will, and you still want to support OpenCV, rep the brand, if you will, you can buy official merchandise at opencv.myspreadshop.com, where we've got 20% off everything right now, including the iconic Import CV2 statement on a shirt, a hoodie, a hat, whatever you want. We've also got the OpenCV logo on shirts, pins, stickers, tote bags, NPR style, and pet bandanas, as well as the I Love OpenCV logo design on everything in English, Espanol, and simplified Chinese. But enough of my yapping right now. I'll be back a little bit later. I think now is a great time to get started. Ali, it's your show. Take it away.
Of course. Thank you so much. So I'm sure that a lot of you guys have watched the first part of this, let's say, series, and we want to continue with the algorithms that, let's say, we talked about. But before that, again, I'm Ali Pahlevani. I'm a robotic software engineer, and mainly most of my works are concentrated on SLAM, and because of that, I love it. And one of the hobbies that I have is to test different algorithms, different, let's say, state of the art SLAM algorithms, and compare them first for myself, and then hopefully for others to whenever they want to choose any SLAM algorithm, they really be easy in doing that. So Phil, can I share my screen?
Yeah, please do.
Thank you.
SLAM is one of those difficult topics, and it is so there are so many options, and that's why some of these things that you're mentioning, I'm going to learn them for the first time as well, because these, the communities, the algorithms, sorry, are moving so fast. There are so many different options, and the thing is that there is not one single SLAM that I will just use it as default. So it's very interesting.
Yeah,
Exactly.
I had never heard of about 3/4 of the things we talked
Yeah,
about last time, so I'm excited for this one too.
exactly. Yeah.
And basically, one of the reason is that some of them are good for some type of lidars. For example, some are good for solid state, some are good for rotating ones, some are good for the places that we have a lot of features in them. And basically, as you just said, there's no just a single one that is fits all of the works, and that's why we should learn how to find the one that fits our work. So. First, please let's have a very short recap of the part one. I think it's necessary. In the part one, first we discuss SLAM, what it is, why we call it a hard problem robotics, and we talked about mapping, localization, and when we need to basically do both of them at the same time, which nowadays is let's say um, 80 to 90% of the time we basically need to use SLAM, not just localization or mapping. And then we talked a little bit about one of the main, or let's say, the recent, not just recent, but the ones that mostly using, let's say, all of the algorithms today, which is post-graph optimization. What's the idea behind it, and why does it need to have front end and back end? Basically. So I won't go into detail of that. And then we basically talked about why sensors are very important in SLAM, and basically what are the overall type or main types of sensors that we get to use them in different situations, from 2D or 3D lidars to different type of cameras, depths, RGB, RGBD, and IMU encoder, etc. So, and basically we understood that sensor fusion is, let's say, the backbone of SLAM. And without it, and without knowing how to do it perfectly, we can't have a good SLAM. The first algorithm that we talked about was Slam Toolbox, which is basically a toolbox, as the name suggests, and it is very, very common. It is very useful. And the good thing about it is that with the minimal changes, we get to use it in a lot of different places, and is basically a 2D SLAM tool. Next, we talk about FastLeo 2, which, as the name suggests, comes from FastLeo 1 with some really great features that have been added to that. And it is very common, and it's used in a lot of different places for real-time scenarios to, let's say, long life mapping and a lot of different scenarios. But one of the things that it doesn't have is, let's say, loop closure. It's main repo, but there are forks that add that to it as well. Then we went to OrbitSlam 3, which is after OrbitSlam 2, that a lot of people may have used it. And this is a great, let's say, tool whenever we want to use different type of cameras for performing the SLAM. So FastLeo 2 basically is for 3D lidars and IMUs. But OrbitSlam 3 is basically mainly for combination of, or let's say fusion of, IMU plus different type of cameras, monocular cameras, stereo, RGBD, etc. And it is widely used and very important to really learn that if we want to basically use, basically perform VIO or VIO SLAM in our pipelines.
By the way,
Then,
a lot of people may not know that orb features, they were invented by OpenCV. Like, it was an OpenCV paper by Ethan Rubley and Gary Bradsky.
yes, exactly. Thanks to
and
OpenCV for doing
and
such a
big
great
shout
job.
out. Also, folks may not know Ethan, one of the primary people behind Space NG.
Yeah.
Thank you, guys. Then we discuss RTAB-Map. RTAB-Map is also one of the ones that I use myself a lot in different situations. And one of the good thing about it is that It lets us combine different type of cameras and lidars, 2D lidar, 3D lidar, different type of, let's say, RGBD and monocular stereo cameras plus IMU. And because of that, it is very versatile, and it has a good ROS2 uh, version that we can use in different projects for indoor and outdoor situations. So this is one of the algorithms that we can, let's say, consider that as one of the main options for any type of work that we want to use. Not just, I'm not saying that this is the last choice that we have, but this is the one of the ones that we can start our work with, and then we understand what are the things that we have to add or remove from that to reach another algorithm. Then we talked a little bit about Gmapping. Gmapping is a particle filter based 2D SLAM algorithm, and because of that, let's say nowadays is not that much used anymore, because nowadays, especially because we are performing SLAM for large environments and for lifelong mapping, we need an algorithm that basically has inherently postgraph optimizations in it, a good front end and back end for lots of different purposes. And whenever we are using a filter based algorithm, especially in here a particle filter based, so, as you may know, particle filter, the good thing about it is that it is multimodal. So, when we are estimating the pose and map, we can, let's say, keep track of different modes of the estimation that we could have, so that finally we, let's say, converge to one of the most probable ones, the one with the highest probability. But when the environment gets bigger and bigger, the number of particles go high, and because of that, it uses too much, power from our hardware and system, and it's not efficient enough. So that's for Gmapping, and let's go to the new one for here for today, which is RESPLE. RESPLE is one of the recent ones, and when I first, a lot of the algorithms that nowadays, let's say, are published, because as you mentioned, nowadays a lot of people are trying to come up with new SLAM algorithms. Some of them are, based on another one with slight changes, but some of them are very, with great innovations. And RESTful is one of the ones that is really great and has really great innovations. And um, as I was saying, whenever I run into one of the new ones, I try to, maybe I don't go into its detail, but at least I try to clone that, try to work with it, and try some raw specs on it and see how it works and what are the results, and compare them to some of the previous one that I have. And this is one of them. So we can say that it's the open source continuous time odometry. So why it's important that it's continuous time? Because a lot of the times when we are performing odometry, we can have discrete time odometry and continuous time. And one of the features of this is that it's continuous time. Basically, it uses BS splines. I don't want to go into its detail because it's not in the scope of this, let's say, presentation. But you can go read this paper. It's really, I think that the mathematics of this algorithm are really beautiful. And some of the times there are algorithms that maybe they are not efficient enough, because in Islam, accuracy is important and efficiency is also important. There are algorithms, especially the new ones, that maybe have good accuracy, but they are not good enough for online Islam or when we deploy them on the hardware. So, but some of them, even the one that are not efficient enough, they have good mathematical insights in them. And if you want to learn about them, if you love math like me, you can go read a little bit about it, and maybe learn something new, maybe not useful for your project, but at least something really cool that they have used. It supports LO, which is lidar odometry, LIO, LiDAR inertial odometry or LiDAR IMU odometry, and multi-sensor setups. And it emphasizes on smooth and more accurate motion estimation without traditional error state complexities. So again, I don't want to go into this detail, but it's really cool. And also in the repo of this algorithm, it has been tested on different great data sets. And as you can see in this video, and this video also, the left one was one of my works that I let's say tested it on one of my ROSPACs. But at right, this is one of the ones that they themselves have made it and have tested it. And if you just check different one of them, you can really see how accurate it maps and how great the odometry accuracy is. Okay, so let's go to next one, which is Slam. So Slam is one of the, let's say, most famous one. And it's not just Slam. There is another one, kinematic ICP, that you will see, and another version which is Slam ICP. I think it was Slam ICP. I'm not sure. I think, or no, it was first it was KISS ICP, then KISS Slam, and then kinematic ICP. We will talk about it as well. But these are some algorithms that let's say a group that are really great and sophisticated and well-known people in this field have come up with them. And some of them are the creators of a great book that recently was published. I will talk about it at the end of the presentation. But Slam is one of the great choices that um, I really suggest to go, because it's very easy to use, as the name suggests. Keep it small and simple. It is a LiDAR only 3D SLAM, which means that it inherently is not for LIO. It's basically for LO, especially for 3D SLAM. And it focuses on robust localization and mapping. And also it has different features like using local map construction and postgraph optimization for correct drift. And what it means is that it is it has a full pop pipeline. Basically, it has a front end and back end, and because of that, it does have loop closures. One of the next algorithm, which is KISS ICP, or a lot of algorithms, for example, FastLeo2 is in this category, that they don't have, as I said, inherently loop closures, meaning that they don't correct the accumulated error from odometry, and they don't correct for the errors for mapping. Although FastLeo2 without that is very accurate, but this algorithm and a lot of other algorithms does have a backend for performing postgraph optimization and basically using loop closures to correct for the drift that have been accumulated. So this is a very good sign of any algorithm that you need for at least a lifelong mapping, meaning that when you want to do a mapping for a long time, or you want to do in a large environment, having loop closure is very important for you. Because let's say if the not performing SLAM for a long time or in a very large environment, maybe using only a robust ICP could be really great for you. A robust ICP, iterative closest point for LiDAR plus IMU. But if the time goes on, and basically when we have a large place to map, basically the time goes up. And after a specific time, we can say that the accumulated error reaches a place that is not acceptable anymore. So it means that when we go for a long ride and we come back to the place that we were, if we haven't done any loop closure, and we've been performing this time for a long time in a large environment, when we come back to the same place, we can see that the odometer result is far off from the place that we started, and that's the accumulated error that we have. And also, one of the other good thing about KISS Islam is that, let me play this as well. Sometimes I forget to play these videos, sorry. Is that with minimal parameter tuning, it is very important. Minimal parameter tuning, it achieves state-of-the-art pose accuracy and operates faster than sensor frame rates. So I said that minimal parameter tuning is important because there are a lot of algorithms that are very great, but you need to let's say tune yourself a bunch of algorithms in a YAML file, in a config YAML file, and sometimes it's really irritating and it's not good enough. It takes too much time from you, and I can say that you won't know if the parameters that you have set are optimal enough or not. But there are a lot of algorithms that with minimal parameter tuning give us great results, and PSSLAM is one of them. For example, another example is again FastLiDAR2. In it, when you want to use a type of LiDAR in FastLiDAR2, you should use the specific type of a specific YAML file as the config file for the type of LiDAR you have. For example, you have a Velodyne LiDAR, you have a RoboSense LiDAR, you have, I don't know, Levox, any type of LiDAR. And the good thing about FastLiDAR2, for example, is that again in it, sometimes you just need to set the calibration values, and that's it. What I mean is that you just only need to do a calibration for temporal and spatial calibration between IMU and LiDAR, and just put the translation vector and rotation matrix in there for calibration, and that's it. And it gives us a very good result. And I believe that that's one of the great things that some people come up with their algorithm, because you have to think about a lot of stuff when you are designing the algorithm, that without that much of tuning, it gives you a great result. Okay, enough with Slam. Let's go to MOLA. MOLA is also one of the ones that I really like. It's very cool, and it has its own UI and UX, and it's very beautiful, I think. It's like a complete package, and one of the good things about it, as the name suggests, it is modular optimization framework for localization mapping. And this modular means that you can use different modules for performing the task you want. For example, um, we can say that most of the algorithm that we have, they have a static pipeline that you just have to provide the topics, for example, IMU topic and LiDAR topic to it, and it gives you a map and odometry. And what I mean is that it is a static, the pipeline, but in MOLA, you can somehow design the pipeline with the existing modules that are available. For example, maybe you don't want to do a loop closure. Maybe in the scenario you want, maybe you want to use different type of sensors. You want to I'm sure that you know what I mean. But in
So,
order to completely understand how it
could,
works, I suggest that you go and install that. It has a binary installation for ROS2. You can easily install that and use a ROS pack and easily test it, especially the UI and the GUI that it has. And yeah, I'm sure that you will love it. For example, in here, as you can see, this is the map that is building. This is the measurement. By measurement, I mean the, let's say, point cloud of the LiDAR. And this is the odometry information that maybe is not, easily seen in here. But if you do what I just said, you will have such view as well for yourself, and you can just check it. And the other thing about it, what else should I tell you more about it, is that it is compatible with ROS2. And this is important as well, because nowadays, as you know, ROS1 is basically end of life. And everybody is trying to migrate from ROS1 to ROS2. But because this end of life is somehow recent, there are a lot of great algorithms that haven't inherently come up with a, for example, in their repo, with a branch for ROS2 compatibility. But there are algorithms that are, newer and more recent, And because of that, they have tried to only come out with the ROS2 version. And I think that's really good because in my projects, there are times that I have to migrate myself from ROS1 to ROS2 for a project, and it's really hard sometimes. And not even that, but sometimes, for example, in Fast Leo, or it was Leo Sam, yes, I will talk about Leo Sam as well. I wanted to work with a type of LiDAR that there was no config file for that because the LiDAR was new and they hadn't thought beforehand. And I had to come up with a new structure for the algorithm to accept the point cloud of that LiDAR. These are the kind of thing that if you want to get your hand dirty, you will most likely get to do them a lot because you will run into the real world problems that a lot of them have stuff that maybe no one has already thought about them in designing their algorithm. So please always try to remember this. So I think that's enough for MOLA. As I said, I don't want to go into details of this algorithm because first I have put more information about each of them in my blog that I will show you at the end, and also the repo for them that you can go and clone them, and also the paper of them that in order to understand what the mathematics are behind them, you have to go and read their paper, because a lot of the algorithm, the result are just like this: a registered point cloud with odometer result. And so lots of the time we can't really understand what are the differences, and that's why you have to go and, let's say, test them yourself and read their papers. Okay, so let's go to the next one, which is Roman. So Roman is also one of the let's say, first of all, it's a recent one. And as you can see in the name, robust object map alignment anywhere. And this anywhere basically means that in their let's say, in their we can say literature, it's a view invariant global localization method. And by view invariant, it means that there are a lot of times that when we see a place, for example, in here, we see some trees, let's say, or a view of a place. We get a RGB image from it, and then when we change the angle, the rotation that we are looking at that place again, because we have changed the view, maybe our algorithm won't be able to recognize that place and understand that, okay, I have already been in here, and this is a loop closure, and tries to add that let's say, loop closure hypothesis to the set that later tries to accept or not. But one of the main concentration of Roman in here is that it tries to, not just tries, actually comes up with an algorithm that is very good at doing that. Meaning that whenever we have different views of the same place, it can easily, um, basically, we can say, easily understand it, recognize that this is the same place that we have been before, even if the view has changed a lot, and adds a loop. And because of that, we will have a good, very great global localization. Because as you know, basically this type of loop closure are great for global localization, meaning that uh, as I said it earlier a lot, when we go for a long ride and come back to a place that we have already visited, if we understand that we have been here and we correct for the errors, this is a global localization, meaning that we understand that where we exactly are in the map with the minimal accumulated error possible. Because when we let's say, when we have a cost function in a postgram optimization, and we try to basically try to minimize that, it tries to minimize the whole nodes, their edges, and as a result of that, not only the drift in the map is enhanced and the drift are removed, but also the localization is enhanced, and we can have a better global pose estimation of where we are right now. So that's very important. And also, it has a very good ROS2 package. As I said, this is very good point. I believe that having a good and modern ROS2 package is a very good point for any algorithm that you run into, even if it is state of the art. Sometimes it is easier to work with it. Um, Although there are algorithms that let's say come up with a Docker installation that using that, even if you don't have ROS1, using Docker you can use the algorithm in Docker. But having a inherent, let's say, ROS2 package is a very good thing that a algorithm can have. And also it improves multi-robot trajectory estimation. This is also a very good point to remember. It means that in here we don't need to only have the different views from one single robot. We can have different robots which share a map, and basically since each of them are looking at the same place, they all have different views. But because the algorithm can handle different views, we can have a global optimization of the map for all of the robots at the same time. So this is also another great points of this algorithm. And I think that I played this, but since I'm not sure, I'm gonna play the game. This is also one of the LinkedIn posts that I have posted. This is I tested the algorithm on a data set that they had provided themselves. And when I checked the odometer result and let's say compare it with the ground truths, I realized that the results were really good. Okay, that's enough with Roman. Let's go to the next one, which is ball. So Balm is also one of the as you see when I go to a new algorithm, I again say that this is also. So the reason is that all of these algorithms are great, even if, as I said, some of them are not that much efficient, maybe in real time works, but each of them have used some type of innovation that at least it's great to test them once and read a little bit about them, and maybe it inspire you for later if you want to come up with your own algorithm. For example, myself, I am trying to come up with a algorithm for myself with some of my friends. Maybe it takes time, but uh, the good thing is that when I have seen different algorithms, I can see, I can understand, I can realize what are the things that are missing in all of the situation, all of the packages, these algorithms, and I try to concentrate on that and try to solve a real problem, instead of just coming up with an algorithm that a lot of people have come up with it, and they may work much better than what I want to propose. That will be just waste of time. Okay, so as the name suggests in here, ball uses bundle adjustment, but in here it uses it for LiDAR mapping. So for lots of you that are into vision, you should know that bundle adjustment basically is for cameras and for vision, and basically it is one level after we can say pose graph optimization, because in pose graph optimization basically try to correct the nodes which are pose of the robot, and then when the poses are corrected for, the maps that come along with them are corrected as well. But bundle adjustment is one level higher because at the same time, with the cost function that it has, tries to removes the accumulated errors in both the estimated pose and also the features. But mainly, as I said, it has been introduced and used for vision when we have different pictures from a single camera or stereo camera, and then we have with a lower frequency than odometry. Basically, we it could be local or it could be global, but basically we make a cost function, and in it we try to try to um, estimate the transformation for cameras in such a way that we minimize the error between the reprojection error and the real measurement. Okay, but as I said, it's basically has been used for images because the logic has been introduced in there. In here, they have tried to adapt it to, let's say, 3D Slam. And the way they do it is that, they try to use the same mathematical architecture, but in the LiDAR region. And it also gives a very good result. Um, it's a robust algorithm for real-time point cloud processing robotics, but um, yet I can say that it's not that much common. Maybe in future more people come and use it, and maybe it gets more, let's say, efficient. But for now, this is not one of the main options. But at least you can go try it and learn about the logic that it has.
Bundle
I'm sure that you
adjustment,
like. Sorry.
bundle adjustment could be very slow, right? I mean, compared to is that why it is at 2 Hz?
Yes, yes. One of the reasons is that exactly because bundle adjustment, as I said, tries to basically optimize for a large number of we can say features, a large number of variables. But postgrad optimization is because we don't optimize for the map, we just optimize for the nodes.
Yeah.
That's much more faster and let us do our work. But bundle adjustment, lots of the algorithm that use it, um, as I have seen, most of them try to use bundle adjustment for local optimization. For example, if we are doing visual inertial odometry, we don't use bundle adjustment for the whole path. After some frames of images that we have, we do a local bundle adjustment, and we reduce the let's say the error accumulated in that, let's say, timeline.
Hmm.
Yes. Okay, so it's enough with ball. Let me play this. So, so what are these surfaces? So I don't want to go into it because I suggest that you go and check it. But it's very easy to basically run it. This is one of the first works that I done. As you can see, it is also in Rust 1, I believe. Yes. And you can easily see that what happens before performing the optimization and after it. For example, when you have a map before it and when you have the map after it, you can easily see that the point cloud, the map, the register point cloud are much more consistent, and you don't have inconsistency in the point cloud, or let's say the map that has been created. It's very cool. Okay, next one is Kinematic ICP. As I told you, this is also one of the other works from the same team of Kiss Slam. Not just exact same team, but a lot of the members are, the same. For example, Dr. Professor Cyril Stashnis, that um, he teaches different courses. For example, Slam for robotics in Bonn University. He has also a very awesome course on YouTube. That one of the first course that I watched, and I loved it a lot. And recently, the book that I just said, he's one of the main contributors to the book. But basically, let me tell you this: that kinematic ICP is, let's say, a algorithm for odometry. So it doesn't have a loop closure, but mainly it tries to give you a great way to combine the measurement from LiDAR and real odometry encoders, let's say, and IMU, so that you overcome the degenerate scenarios. So that's very important. What are degenerate scenarios? Each type of sensor has some type of degenerate scenarios for itself. For example, when we are dealing with cameras, a featureless environment, For example, a wall with repetitive patterns, or a wall which is just one color, it doesn't give us enough feature to distinguish, to you know to match the features, to add this descriptors and that kind of stuff. And we can't, let's say, make a good odometry or even SLAM in that degenerate scenario for camera, or a place with low illumination. Again, a camera can't perform well in there, because when we don't have good illumination, we don't detect enough features to ever work. For lidars, there are other type of degeneracy. For example, when we are going in a long corridor, again, when we want to do ICP, or iterative closest point, which we try to find the transformation by matching to two. For example, if you're doing a scan to scan, by matching to a scan of the LiDAR in a long corridor, because we don't have enough features, we don't have corners to distinguish between different places. All of the wall is just, let's say, we have a local, we the estimation is not good enough, locally good, and also finally globally good. In those scenarios, maybe lidar is not won't be able to give us a good odometry and then a good mapping. But whenever we are performing maneuvers, and we are looking at corners or doors or places that can be distinguished, basically lidar can work much better. In IMU, for example, the more agile that we move, IMU cannot give us better results, because when you have more acceleration and angular velocity, the let's say the value of acceleration gets much bigger than the noise, and that ratio goes high, and because of that we get rid of the noise and bias. But in the places that we don't experience that much acceleration or angular velocity, the accuracy gets a little bit worse than that situation. For encoder, again, when we are going in a straight line, encoder can give us really great estimation, pose estimation. But when we are, for example, performing when we want to perform rotation, because we could experience things like wheel slippage. That wheel slippage can basically introduce error, and when we add that error and we go on, the errors accumulate, and after a time they basically get a very bad estimation for wheel encoder. So as you saw, different sensors have their specific degeneracies, but when we try to very, let's say, with great thoughts, combine them, and for the time make the algorithms adaptive. For example, when we have a degeneracy for wheel, we try to rely more on IMU or LiDAR. When we have a degeneracy for LiDAR, etc., vice versa. And this is something that we can do, and by doing that we will have a very robust and adaptive algorithm. Kinematic ICP is one of them that does something like that in one part, for the degeneracy that I told you between wheel encoder and um, LiDAR. And also one of the other things is for the word kinematic. As you see in here, it means that it adds the kinematics of the vehicle to the estimation process as well. And one of the good thing about it is that let me tell you how it works like this. For example, when we don't know about the kinematic and only rely on the measurements, we have different distributions that can be, let's say, multiplied by each other for LiDAR, for ICP, and for IMU, for example, and wheel. But when we add the kinematics of a vehicle, for example, this is a 2D vehicle and it has a specific kinematic. When we add the mathematics and kinematics of that to the process, it doesn't let the distribution go anywhere they want. And it means that, for example, if the kinematics of the system tells us that by this speed, by this kinematics that we have for this vehicle, we can't go, for example, faster than this, and we can't jump from this place to another place. It gives us a probability distribution that multiplying that by another one from another, for example, ICP, gives us a much more accurate estimation for the for the process that we have. So that's also one of the good things that kinematic ICP introduces. How they exactly work, you should go and check the paper. That's very cool, but that's also one of the great ones. This was also one of the tests that I did. I tried to compare the odometry result from wheel IMU, from wheel ICP, and from wheel IMU ICP. And I added the accumulated errors and showed that in this algorithm, basically when we have wheel IMU ICP, the accumulated error is lower than when we have wheel ICP, and that will be again lower than when we have only wheel and IMU. Mainly ICP gives us very great results. Okay, so let's go to the next one, which is mints. So I first wanted to introduce another one, but it's okay. Let's go with mints. Mints and open bins. Open bins comes in here, yes. Mints and open bins are two really great, let's say, visual inertial odometry algorithms that basically nowadays they have also added loop closure as well. I'm not sure. I think that last time that I used it, they had added loop closure, I think. But anyway, it's a very great algorithm for performing basically visual inertial odometry at first, meaning that we use and we combine the vision, the images from a monocular or stereo camera plus IMU, and use the combination of their measurement, because IMU, the good thing about it is that it gives us high frequency measurements, and whenever we have a dynamic motion, we are doing agile movement, for example, in drones or race drones, it is very important to have a high frequency IMU, like at least 200, but for that it could go up to 400 and even more than that. And that lets us, let's say, keep track of the fast motion, and not just fast, basically dynamic motion that the vehicle has, because there is a difference between when you are moving fast and when you are moving agile. Going fast, it means that you have a high velocity, but maybe you don't have acceleration. So you're not moving agile. But when you are, for example, turning a lot, and you, for example, in drones, they suddenly go up and down and do a roll pitch yaw with high rates, it means that the movement is very agile. And using IMU in there is very necessary, because IMU, as I said, three acceleration for accelerometer in the IMU, let's say, can take the information for acceleration along x, y, and z axis, and for rotations, there's a gyroscope in it, a MEMS gyroscope that can take into account the angular velocity about the x, y, and z axis. So when we are moving very agile, it's very suggested to use IMU. Means one of the things that it has with respect to OpenVINS is that OpenVINS is basically for visual inertial, but in here they have also added other sensors as well. You can, for example, use GNSS, which is GPS, for example, wheels, meaning that wheel encoders, and LiDAR as well. So that's a very good thing to use MINS, because later when we talk about OpenVs, you will see that that's mainly concentrated on vision and inertial. Okay, and I don't have any video
Let's
in here.
Ali, let's do me a
Also,
favor. Let's pause here. How many more algorithms we got to go through today, if you don't mind me asking?
like 4 or 5. There are 2 ones that I added,
Okay.
Leo Sam and Lego Loam.
Cool. I think
Should I pause?
let's pause, and I mean, I think we might have to make this a 3-part episode. I think we've got enough algorithms to go through for a whole other episode. It might not be for a few weeks because we are pretty well booked. I think we should be able to get it in before the end of November, though. So I think let's do that. But right now, let's pause and do our trivia giveaway. So if you are new here or you just need a little reminder, one of the things we do on OpenCV Live is give away a free OpenCV University course to you out there watching. I'm going to ask a trivia question based on today's presentation, and the first person to answer that trivia question correctly in the chat, wherever you're watching, will win the OpenCV course that you would like. I'm going to go ahead and share my screen here and show you a little bit about OpenCV University. While I do that, Satya, would you like to talk a little bit about OpenCV?
Yeah, so OpenCV University is, are you going to switch? Okay, yeah.
Yep, there we go.
So you can go to OpenCV University by going to opencv.org/university. And this is a series of courses that take you from a regular programmer all the way to an AI expert in computer vision, right? So the emphasis is computer vision, obviously. And we have a series of about 6 courses, out of which 2 are what we call foundational courses. One teaches you the fundamentals of traditional computer vision, image processing, everything, which is called Fundamentals of Computer Vision and Image Processing. And the second one is a deep learning course. And the deep learning course you can get in 2 flavors, PyTorch or TensorFlow. And these are bulky courses, right? These are not for people who want to get a flavor of computer vision in 2 weeks. So these courses take time. So the foundational courses, you'll spend about 3.5 to 4 months if you're spending about 1 to 1.5 hours every day. So that's the amount of time it takes. So 2 foundational courses, you'll spend about 7 to 8 months to complete it. But once you have done it, you will have the necessary knowledge to call yourself a computer vision expert, right? Especially in the fields which like classification, object detection, segmentation, etc., and all the traditional computer vision methods, except for the 3D computer vision, 3D reconstruction, etc. But other than that, it's a very solid course. You can consider it, similar to a master's level program, much more than that actually, because most master's level programs do not cover this much material. But this is for serious people who are interested in a career in computer vision. So check it out. And if you do not know, if you want to just dip your toes, we also have a bunch of free courses. These are 3-hour courses. Don't expect miracles. But if you want to see whether you want to, have a career in computer vision, these courses are very useful. These are called boot camps. 3 hours or so is what you're going to spend.
Yes, indeed. Thank you for that, Satya. We've also got, I'm going to go ahead and solo myself here. Today's sponsor, today's episode is brought to you by the newest OpenCV Silver member, the British Machine Vision Association and Society for Pattern Recognition. That's the BMVA. You can find their website at bmva.org. I'll go ahead and bring it up on the screen here. So bmva.org, and in fact, we've got a handy dandy QR code. If you want to go ahead and scan that QR code or go to bmva.org to learn all about the British Machine Vision Association. Importantly for them, they've got coming up the 36th British Machine Vision Conference, November 24th through 27th in Sheffield, United Kingdom. Gold sponsors by Tavis and silver sponsor Ncord, supported by the University of Sheffield School of Computer Science. You can find all the information about that at bmvc2025.bmva.org, or just go to bmva.org and click through on the homepage there. If I could afford the flight out there, I would definitely be going to this, but we are so happy to have the BMVA as OpenCV members, and you can look forward to seeing a lot more collaboration between our two groups coming very soon. Follow the British Machine Vision Conference on Twitter at BMVCConf. So yeah, enjoy that. We hope you'll check out the conference if you're in the United Kingdom or nearby places, maybe just a train ride away, and send us your thoughts on the event after the event as well. Welcome, BMVA. Any thoughts on that, Satya, while I'm here? Yeah.
One of my very good friends is a professor at University of Sheffield.
Okay, name drop. Who is it?
Dr. Pinaki Bhattacharya. I think he's in mechanical engineering or something.
Okay.
Yeah. So I have been to Sheffield. I visited him last time I was in UK, or the only time I was in UK.
Okay, right on. Love to hear it. Yeah, so I'm about to ask a trivia question. The first person to answer, I'm bringing up all of our chats here so I can see the first person to answer. The first person to answer either in Zoom, if you're watching on Zoom, make sure your messages are set to everyone, not just hosts and panelists. I'm going to bring up our question right now. I went fancy this week. Let me know what you think of the new format here. So earlier in the show, we talked about a whole bunch of SLAM algorithms. I'm going to single out one of them. What does BALM stand for? What does BALM stand for? B-A-L-M. What does it stand for? B-A-L-M. Oh, I think we got one here over on Zoom. I'm double checking here because I forgot what it stood for. The answer is yes. Okay, our first correct answer looks like Balveer Singh over on Zoom is our winner this week. The answer we were looking for was bundle adjustment for LiDAR mapping. Bundle adjustment for LiDAR mapping. Congratulations, Balveer Singh over on Zoom. Please send one email to phil@opencv.org and you will win the, along with the name of the OpenCV University course you would like. So go to opencv.org/university, choose a course, and we will make sure you get that course in your dashboard. Congratulations.
Congratulations.
What did everybody think of this hastily put together graphic that I made?
Oh, it's perfect.
All right. So we've got a bunch of questions here today, and a little bit of, I think we'll take a little bit of time to answer these here. Lakshay over on YouTube, you were really close to winning the trivia this week, but Balveer was about 5 seconds faster on the draw. So let's pull up some questions, shall we? First of all, I feel like we got to answer this one every episode, but I'll keep doing it if they keep asking it. Do you upload these videos after the live? Yes, we absolutely do. These are available on the official OpenCV YouTube channel. You can go there, in fact, and become a member by scanning the QR code there that just popped over Satya's face. Scan the QR code or go to @OpenCV official on YouTube. That was not on purpose, but it's very funny. @OpenCV official on YouTube. Every single episode of OpenCV Live, all 187 of them, I think this is. Hokey smokes, we are marching toward 200. But yes, please, @OpenCV official on YouTube. Those will be there. I've got a few questions here. One from Indra on Zoom. Let me bring this one up. Which SLAM algorithm would you prefer in autonomous vehicles whose main task is to navigate around in off-road environments where they may encounter obstacles like trenches, negative obstacles, and some rain puddles. I'll propose this one both to Ali first and then Satya.
Of
Ali,
course.
you go. I have no idea.
Of course. So one of the things that you have to consider is really important is the type of LiDAR you have, because some of the LiDAR, especially for the solid state ones, for like RoboSense, they are not supported in some algorithms. But generally, I again say that FastLeo2 is very good. LeoSam is very good. LeoSam is also the good thing about it. We didn't talk about it today, but LeoSam does have a good loop closure, and it does include postgre optimization. So definitely for lifeline and large environment and outdoor, as you just said, with different obstacle is a very good choice. And these are the two ones that you can. And one thing to remember is that there are lots of different forks from these algorithms that maybe have been adapted. For example, for FastLeo2, you can find a very great fork for having relocalization, and another one that adds loop closure to it, and another one that adds, for example, RoboSense or some other type of sensors, LiDAR support to that. So when I say these two algorithms, it could include lots of different forks from them.
All right, thanks for that. Yeah, I mean, generally, it seems like a cop-out sometimes on this show because people will ask questions, and the answer is often, it depends. And I think, especially with SLAM, there are just so many choices out there that to really get your use case, perfectly, you're probably going to have to do a little bit of custom work. You're going to have to take something, you're going to have to make it do exactly what you want. And I think that's the case with a lot of these.
I have a question for OpenCV. Let's say we decide to implement the state-of-the-art algorithm for Visual SLAM in OpenCV, right?
Mm-hmm.
Which one would you recommend? And is Visual SLAM, just Visual SLAM, enough? Are there enough, applications where it would be useful? Or we should use more, like at least add an IMU, maybe add a LiDAR support as well. What is the minimum that would be good enough for OpenCV, an implementation of OpenCV, and which algorithm is, in your opinion, the best?
That's a really good question. I think maybe we'll send out some kind of like survey to the newsletter about this. But yeah, Ali, thoughts on this? What Satya just asked. I mean, we have talked about this a bit just recently. In fact, it's fortuitous that we would be having this conversation, but internally at OpenCV about SLAM implementations. If you could briefly summarize again, Satya, your question there.
Well, the question is Visual SLAM enough for a large number of applications, right? Even if we don't add LiDAR, etc., LiDAR support, etc., just complete just Visual SLAM, right? So that's question number one. And if that is true, then what is the best algorithm right now? What represents the state of the art right now for that? And we can take this offline also, right? If you need time to think about it. But my point is that I'll get in touch with you to discuss this thing, right, in great detail, so that we can select an algorithm which will be useful for a lot of people.
Okay, so let me answer your second question first, because I can answer that right now. About is only Visual Islam enough? In my opinion, no. And there is a very big debate between people that say, the people that like Elon Musk, and they only want to use cameras. But Mark Rober did great tests, as you have seen it, and it proves that in a lot of situations, vision only cannot just be good enough for us. For example, in a lot of hard scenarios or foggy scenarios, or the ones that you have seen. And on the other hand, LiDAR gives us very good and detailed maps, and it is great for lots of different degenerate scenarios, but it comes with its cons as well. So one of the bad things that a lot of people say is that it needs it is mechanical. But now see there are a lot of solid state ones that are coming into the market that are very high grade, and they don't have any rotating mechanism,
Yeah.
and they are like a grid base that for example, you divide based on the field of view, vertical, horizontal, that you have. Using that, lot of answers, lot of scenarios or degeneracies have been answered by that. But I can say that vision only is not enough. If you want to concentrate on your work, at
Yeah.
least you should have IMU as well, at least.
Got it. Got it. And yeah, the thing is that the what you mentioned is that the moving parts. I think so. I have a vacuum cleaner, the Roomba kind of thing. It is not a Roomba, but it's a different company. But it uses LiDAR and it doesn't have any moving parts, right? It has it's some kind of static LiDAR.
Yeah, exactly. That those are, for example, there are ones, as I said, are solid state, and those ones that these vacuum cleaners have, their field of view horizontal is not, is like I can say like 90 or 120, but there are much better ones for RoboSense, especially that it gives us a 360 field of view horizontally and 90 degrees vertically. That it's very good, but the cons for that is that lots of the time the range that it can detect gets lower, because the overall energy is divided by the number of points that you have. So you
Right.
have to one that gives you good range and also good field of view.
Hmm. Got it. Got it.
Yes.
All
And
right.
for the other one, if it's okay with you, I can think about it more and
Yeah.
come up with a better answer, and even we can get in contact and talk about it more.
Right, right. And the thing is that adding IMU is not that not so IMU requirement is not that tough, right? Because most of the people have cell phones, right? They can actually gather this thing, and all cell phones have IMUs, right? And some have LiDAR also.
Yes, but IME should be a high grade, because if it's not good enough, the noise characteristic could be bad, and
Yeah.
the error accumulated is not good enough. So maybe IME from phone is not sufficient enough for
Oh,
a slam problem.
got it. Got it.
Might need to talk to our friends at Bosch about that.
Mhm.
All right, we've got a few more questions here. Thank you so much for that, Ali. Detailed answer, and we'll definitely talk a little bit more off the show here. We've also got this one I thought was really interesting. One of the things, maybe for the third episode at the end, we could put a little chart or something. Lakshay on YouTube wants to know how much computation all these algorithms take, and I think this is one of those one of the metrics that helps people decide which of these off-the-shelf algorithms to use is based on how much compute they need to throw at it for their use case. And so I'll rephrase this slightly and say, from your perspective, what are some of the more computation light SLAM algorithms and some of the more computation heavy SLAM algorithms?
Okay, so it is one of the questions that it really depends, because uh, the first, let's say, thing is that are we doing a 2D mapping, or are we doing a 3D mapping? For example, if we are working with 2D LiDAR, so we have only a cross section. When we are doing 3D LiDAR, we have also different, let's say, different layers of points. So suddenly, the amount of computation that we need go so much high. The other thing that is very important is frequency. If you have a 10 frequency IM LiDAR, or 20 or 30, that's something that is multiplied for each second by the number of points or number of beams that the LiDAR has. And for camera is much worse, because you have a frame, and if you have 20 hertz for that, so it is multiplied by the amount of pixels that each image could have. And again, it depends on, for example, in camera, if the image is RGB or if it's grayscale. So that's the other thing that's important. And finally, the other thing that really contributes to this is the number of the sensor that we are using. As we just discussed, if we are using only a 2D LiDAR, for example, there are a lot of scenarios that we only use 2D LiDAR plus a not that much high grade IMU. So in those situations, for example, in a factory floor, that there are not that many, the movement of the forklift, for example, is not that much agile. So in there, we can have lower frequency for LiDARs. We are indoor in those situations. So when you are indoor, the range that the LiDAR needs to, get the information gets lower. And also, uh, for IMU, again, we won't need that much high frequency IMU. And a combination of this means that we can have low computation, relatively, I mean, low for those situations. But for a car, it gets much more because we need higher frequency. We need much more number of sensors. For example, we should have different cameras with different field of views. One, for example, in front, one in both sides, one in back. And also we could have radar, IMU, and GPS. And the combination of this could add much more to the amount of computation that we need for car. And finally, one other thing is, let's say, the back end. So as I said, when we have a backend for our algorithm, that means basically for a post-graph optimization we should have. It also depends that what is the frequency of backend, meaning that what is the frequency that we are solving the cost function and are minimizing that, and also the number of variables that we are minimizing in backend. And if the number of variable go high and the frequency of backend go high, based on the sensor that we have, it could also add to the amount of computation that we have. So I hope that I could answer this
It's a
question.
very tough question because the variations are so many.
Yes, definitely.
Yeah.
That's the hard thing about it, because you have to think a lot to choose which one to use for your project.
Phil, you are on mute.
There's a reason that this is some people's full-time job, is figuring out SLAM stuff. So we've got, I think, let's do one more question here and we can call it a day. From Cal on Zoom, if they would like to buy some hardware to play with all of these algorithms, what is a good medium-high option? So like, I would say the prosumer choices for some maybe robotics platforms or some kind of medium-end hardware. Do you have any thoughts on this, Ali?
Yes. So first of all, Raspberry Pi hardware, for example, Raspberry Pi 4 or 5 with 8 GB of RAM or higher are a good starting point for us, because we can install, for example, Linux 2204 or 2404 on it. We can install ROS 2 with the latest versions, and we get to work with a lot of algorithms. But if we need a higher end GPUs, for example, we can go for Jetsons, Jetson Nano, Jetson Orange, and they are also very great options based on the budget that you have. These are, in my opinion, two great hardwares that you can buy. And for example, the type of Jetson that you buy, it depends on your budget. The more you pay, the better result you
So
get.
are these algorithms optimized for the GPU? Like they are able to use GPU processing, a lot of them?
Yes, some of them, yes. Some of them, yes. Some of them are only CPU based. Some of them are, for example, have two versions for CPU and GPU. You can enable, disable.
Yeah, and that'll definitely affect some compute, some battery usage, et cetera, et cetera. So yeah, I think, man, we're about 20 past the hour here. So we're going to do a episode 3 of our deep dive on SLAMs with Ali from SLAMbotics here. Look for that probably sometime in November based on our calendar availability here. We had to reshuffle some things. So next week we will be back with, will we have time to put together the OpenCV 3D presentation, Satya?
Yes, yes.
Okay, excellent. So next week we will have, will Gersimer be joining us next week?
Yes,
All right, so we'll have Gersimer Singh from OpenCV. We'll be talking a bit about some of OpenCV's recent work in 3D. We're moving out of 2D and into 3D, or rather we're expanding into 3D. So that'll be fun. Doc, you want to go ahead and take us home?
Yeah, thank you so much, Ali. It was a pleasure seeing so many different algorithms, and we are very excited for the next episode also. And thanks our audience for this, for showing up every week, because it gives us a lot of pleasure sharing our thoughts as well as the knowledge with you and connecting with you on this webinar. And as always, thank you, Phil. This went smoothly. A job well done, as always.
Thanks so much, Doc. And yes, thanks so much to you out there watching and to our generous guest with both his time and expertise. We will see you next week, Thursday, 9 a.m., same bat time, same bat channel. Take care of yourselves out there, folks. Take care of somebody else if you can, and have a great day wherever you may be. Adios.